Okay, we haven't only run into the absolute value parent function, we've also tackled the quadratic and cubic parent functions, and throughout the quarter we'll be adding exponential and log and rational and radical, so we'll have a whole collection. Quadratic actually come with their own kind of interesting issue, and we'll tackle it in one way now. We won't really address that same issue for cubics because that's something that we'll tackle in 142, where we work on a different strategy for graphing polynomials. So the problem with quadratics, and it's not a huge problem because we've already studied, hopefully in the past, previous ways to graph quadratic functions, so we have some tools. But it would be nice to see that transformations also work on quadratics, and they do. It's just that they have to be written in a particular form. So if you get a quadratic in standard form, what we're looking at right here, in ax squared plus bx plus c sort of form, you can't tell what the transformations are. That's written so that it's a combination of like an x squared parent function and an x parent function. You can't have both an x squared and an x floating around if you want to be able to see transformations. So we really want to end up in what sometimes in algebra is called vertex form. So it's like a y equals a times x minus h squared plus k. And it gets called vertex form in algebra because when it's in that form, you can just read the vertex off. But the truth is what you're really doing there is reading the transformations off. H is a horizontal shift and k is a vertical shift. So your vertex starts at 0, 0, and the only thing that will move it is those two shifts. So those shifts tell you exactly where it lands. Our big goal for this section is to figure out the trick that we need to rewrite in vertex form. And hopefully you've done this algebra trick in the past as well, but we will go through it from scratch. It's often a fairly rusty one for people. So first thing I'm going to do here is rewrite this with a y, just so that I don't have to rewrite f of x over and over again. If you want to leave it f of x, go for it, but I'm going to get rid of it. What we need to do is complete the square. We need to build a perfect square trinomial in here so that it factors into an x minus h squared sort of form. And the way that you do that, there's actually a few different ways to set this up. So the way I'm going to set this up is I'm going to first isolate the x squared and x terms. So this is kind of just mental. I'm thinking of separating off the negative 14. And then a really important step is you need to get rid of that coefficient of x squared. It's really confusing trying to complete the square when you have a number in front of your x squared. And the easy way to do this is just to factor it out. So we'll end up with an x squared minus 6x in the parentheses. And I'm going to leave some room because the next step involves adding something in there. So it's very easy to double check yourself on this. Make sure you factored it out right. Just distribute that negative 2 back in mentally and we'll get a negative 2x squared and a positive 12x. So that's looking great. Okay, so this is the kind of the magic step. This is the step where we just figure out what is it that we need to add on to an x squared plus or minus ax to make it factor into a perfect square. And the answer is you have to take this number right here, including its negative sign, and you have to cut it in half and square it. And if you're interested in more of why that's true, let me know. I can absolutely share a little bit more detail. I'm just doing a quick reminder of the steps here, but if you want to know more, I can give you more. So negative 6 divided by 2 is 3, and when I square that, I get 9. So I need to add 9 in those parentheses if I want this to factor into a perfect square. This is not a big deal. The problem is when I add a 9 in there, I've actually changed the function. It doesn't look like what it used to look like, and that's not really helpful when you're trying to graph. So we're going to use a very famous algebra trick that we don't actually get to use that often. It's really handy when we do, but it's one that doesn't sneak up that much. You see it a little more in calculus. One that we use a lot is multiplying by 1. So like to change the denominator of a fraction, we might multiply by 2 over 2, and that's always legal because multiplying by 1 doesn't change the value. The one that we need here is adding 0. So what we want to do is if we add or subtract something in the equation, we then need to also do the opposite. So right here, I'm kind of thinking I added 9, but you have to be a little bit careful. What you really did was subtract 18, right? -2 times 9. If you distribute that back in, you've subtracted 18 from the equation, which means you also need to add in 18 to the equation. So what we end up with is y equals -2. And then if we've done this carefully, inside those parentheses should factor into a perfect square. So we want x and x, and then 9 does split nicely into 3 and 3. And if we want that -6 in the middle, they both have to be minus. The two factors are identical, so that is a perfect square. And then conveniently, when we use that add 0 trick, we also figure out the correct k value, the vertical shift. So -14 plus 18 is just +4. And I'm just going to take one more step to rewrite the perfect square with square notation so that it really does look like my vertex form. So that's your goal. So if you need extra practice on Complete the Square, let me know. If you want more background info on Complete the Square, let me know. You should have a little bit of this built into your assignment so you do get to do some practice. You will need to be able to do this if we're going to use transformations on quadratics. Now that I've gotten here, I'm going to work on the graphing part. So when I look at this, I am seeing a multiply by -2. I'm seeing a subtract 3, I am seeing an add 4, and I am seeing this square up here. The square is the parent function. Squaring is not a transformation. So I want to start with y equals x squared. So I'm imagining my parent function, the parabola. 0, 0 is going to be a really nice point to follow on that, and then maybe pick out some variety, so something like 1, 1 and -2, 4, for example. You pick out your points. They don't have to be the exact same points I would pick out, but do try and get some variety, and I think it's really important to follow the vertex. So 0, 0 I think should be one of your points here. When I look back at this, I'm actually going to split it up even more. That negative is out in front. So remember, you can use the order of operations or you can use the parentheses. They do actually show up on a quadratic or a cubic when it's written in the right form. So inside the parentheses is a -3. That will be horizontal shift. Everything else is outside of the parentheses and will be vertical. The negative sign flips all your y's, changes their sign, so that is a flip or reflect over the x-axis. The 2 is a vertical stretch. The -3 is shift to the right. That's with x's, so it does the opposite, and I should say the vertical stretch is by 2. We really will multiply all of our y values by 2. And then last one, we need to shift up 4. We're adding 4 to our y values outside the function, so that'll shift our graph up 4. Okay, so I didn't give myself a grid, and you won't always have a grid, so this is fine and great, I think, to see. Let's go ahead, since I color-coded the first two together, let's go ahead and do them together. It wasn't actually on purpose, but it'll work. So let's see if we can flip upside down, which is multiply your y's by -1, and vertical stretch, which is multiply your y's by 2. So we want to flip and double our y value. First, the flip will take 0, 0, and it won't actually move it. So 0, 0 is still sitting at 0, 0. And then vertical stretch doubles that y value, but it's still sitting right at 0, 0. So I'm expecting it to be upside down and taller, but 0, 0 is right on the flip line, so it's going to stay there. 1, 1, when I flip upside down, will land at 1, -1, but then when I double the y, it will land at 1, -2. And -2, 4, when I flip upside down, will end up at -2, -4, but then when I double, it'll end up way down at -2, -8. So I might want to adjust my scale a little when I'm graphing, and I also feel like I'm a little crooked. So now I have a taller looking version of my original parabola that has flipped upside down. From there, I'm supposed to shift right 3 and up 4, and I actually think I'm going to try and do that pair together as well. You do not have to. You can always do transformations one at a time if you prefer, but it is a little more time consuming. So if you get comfortable, I think it's great to try and combine some of these. Remember that our big goal here is to just get really familiar with how graphs move so that when we're looking at an equation, we have a pretty good picture in our head of the graph. It doesn't have to be absolutely perfect. So while we do try and be precise as we're learning transformations, it's really more for us about getting a good rough idea in our head of what the graph looks like. So my last graph, I'm shifting up 4, so I'm going to give myself a little bit more room above the axis. So let's say this is 1, 2, 3, 4, and 1, 2, 3, 4, 5, 6, 7. I think that should be enough. And then we're going to shift to the right 3, so maybe we want a little bit more room over here. 1, 2, 3, 4, 5, 6. As you're doing this, if you're sketching your own grid, do label something for me. You don't have to label every single tick mark, but if you don't label a tick mark on the x-axis and a tick mark on the y-axis, at least I'm not going to know what your scale is. So I'm actually going to label one at the top and one at the bottom for each. This was way down at -7, so that would give me an idea of what your grid is. Okay, I'm going to start with 0, 0. Here, let's do it with the highlighter. 0, 0. I need to shift to the right 1, 2, 3, and shift up 4. So that will land at 3, 4. That's a nice, easy one to start with. 0, 0 is always a good one to shift. I also had the point 1, -3. If I shift to the right 3, we're going to end up at x equals 4. And then if I shift up 4, we'll end up at y equals 1. So 4, 1 is my next point. Let's see, -2, -8, so that's kind of off the bottom, but I can get the idea here. If I shift, I'm going to shift up 4 first, so that would take us to 1, 2, 3, 4, -2, -4, and then if we shift right 3, we're going to land at 1, -4. Okay, so from here, it's just being careful about connecting the dots. Remember, the vertex landed at 3, 4. So I'm going to start from the vertex, and I'm going to go to the right and down through that point. And then I'm going to go to the left and down through that point. So label carefully. It's okay if everything isn't perfect, but try and keep that parent shape. I won't be upset if it's not a perfect parabola. I will be upset if it looks like an absolute value, if everything turns into straight lines, if things that are nice and smooth end up with sharp corners. That will bother me a little bit because I won't know if you're realizing it should look like the parent function. Otherwise, I think we're good with this one. Thanks for watching.